Okay, let's talk about temperature and some of the thermal properties of matter. So first thing, what we mean by temperature is really what's measured with a thermometer. It is a quantitative description of the hotness or coldness of an object. This is really tied into what we think is hot and cold, but it's really similar to kind of how we defined mass to be a quantitative description of inertia. Temperature is a quantitative description of this hotness or coldness. It's different than heat. It's very important that we know that it's different than heat, which we'll talk about later. So the way that we can measure, we can quantify this hotness or coldness or changes in the hotness or coldness is by investigating some of the thermal properties of different matters. So take, for instance, this thermometer that we have in the picture here, that is has in the base of it, it is filled with an alcohol that is dyed red. And we know kind of how much it will expand when we increase its temperature a certain amount. And then it has in the center of it a hollow cylinder that allows this alcohol to move upwards. Now, because we know the properties of this alcohol, once it reaches a certain length, let's say it stops right here, then we can calibrate this thermometer to know exactly what temperature that is. So we take advantage of the fact that the fluid expands as we increase its temperature in order to get what that temperature is. And we refer to this at some baseline level, which we'll talk about in a little bit, but we really use this thermal property to find the temperature of something. There's other indicators that we have. You can look at something. If it's glowing red, it indicates that it's very hot. So there's other thermal properties as well, but expansion is the one we typically use the most. Another kind of instance of thermal expansion that we use, like in households and thermostats, is shown here in this. We have this strip that's bimetallic. There's two different metals here. So we have a blue metal and we have the kind of this golden metal. Now, when they're at some reference temperature, T naught, they're both the same length. But as we increase the temperature above this reference temperature, we see that the properties of the blue metal are such that it expands at a faster rate than this golden colored metal. So what happens is that since it's expanding at a faster rate, the blue metal must then be longer than this golden metal. And so what happens is that it must bend. So we use this. Maybe we have a little point, something that a good conductor of electricity here, and when it touches this, it tells the thermostat to turn off or turn on, depending on what's going on there. So we can use this kind of for an automated thermostat. So it's another way that we use the expansion property of materials or matter when its temperature increases or decreases. So we defined temperature to be this a quantitative description of hotness or coldness. And I made that analogy to mass. And mass, we said, well, here's 1 kilogram, and that's a big chunk of platinum iridium alloy. In the International Bureau of Standards outside of Paris there. And we just said that is 1 kilogram, and everything is built off of that. So it's just some standard. We do the same thing with temperature. We have some sort of standardized scales, and we say, all right, there's our reference temperature, and we can measure changes from that, with our thermostat here, or with our with our thermometer, we can measure these changes. So we have a couple different scales. There's 3 shown here. So the first one we have is the Fahrenheit scale, shown on the top. This is degrees Fahrenheit. And Fahrenheit, it was just set that the freezing point of water was set to be at 32 degrees Fahrenheit, and the boiling point of water was set to be 212 degrees Fahrenheit. So in the degrees Fahrenheit, there's 180 degrees separating the freezing point and the boiling point. This is used pretty much exclusively in the United States. Then the next one we have is the Celsius, or the centigrade. Centa meaning 100, grade short for graduation. So this one has 100 graduations between freezing point of water and boiling point of water. So we see that 0 degrees Celsius is the freezing point of water, and 100 degrees Celsius is the boiling point of water. So this one between freezing and boiling has 100 degrees Celsius. So 180 Fahrenheit, 100 degrees Celsius. So with this, you can see that actually the graduations in Fahrenheit are much smaller than they are in Celsius. There's more of them, almost twice as many, actually, or 9/5 times as many. So there's a relationship between them, and you can see this here. Fahrenheit starts out at freezing water is 32. The temperature in Fahrenheit is equal to 9/5 of the temperature in Celsius plus 32 degrees. So TF being your Fahrenheit temperature, TC being your Celsius temperature. The conversion between Celsius and Fahrenheit then is just rearranging and solving this, is going to be 5/9 of the Fahrenheit temperature minus 32. 5/9 of the difference between the Fahrenheit and 32. So these are the conversions between these two. Now, both of these start out really just water is the key reference point here. But we have another scale called the Kelvin Scale. It's shown at the bottom here, which is more of a scientific scale, I guess. So this is the Kelvin. And the way the Kelvin scale works out is that we took the Celsius scale and we extrapolated. We said we didn't want 0 to be the base of this new scale. We want it to be this theoretical absolute 0. So the way that the scale came out, the standard for the Kelvin scale, is we took a bunch of experiments and we took a bunch of ideal gases. So we have gas 1, gas 2, gas 3, gas 4. And as the pressure is reduced over here, so we have pressure on the dependent axis and temperature on the independent axis. As the pressure is reduced, you can see that they follow a linear relationship down to a certain temperature. And we found that if you can get down to 0 pressure, if you take it all the way down, this is actually where the pressure is equal to 0, then the temperature would fall. We haven't actually been able to get below this. This is as far as we've been able to go. All these dots here represent extrapolations. But if we extrapolate them, we see that the temperature goes down to negative 273.15 on the Celsius scale. So this is what's known as absolute 0. It's a theoretical 0. Has not been attained. So this new scale, the Kelvin scale, is the Celsius scale, but it's just moved back to this new, the 0 point is absolute 0, instead of the 0 point being where water freezes. So we see here on this Kelvin scale, 0 is this absolute 0. It is this theoretical where everything stops. All these gases would stop moving. They would go to pressure of 0. So all motion ceases at 0 on the Kelvin scale. And then, of course, the boiling point, or sorry, the freezing point of water would be at 273.15 Kelvin. And then the boiling point would be another 100 degrees beyond that, so this would be 373.15 Kelvin. So the size of the graduations on the Kelvin scale are exactly the same as the size of graduations on the Celsius scale. The only difference is that they are shifted down so that 0 on the Kelvin is absolute 0. So our conversion here, temperature in Celsius, would be your temperature in Kelvin minus 273.15. Or you can say here your Kelvin temperature is your Celsius temperature plus 273.15 degrees. And these are the conversions between them. There's also another scale, the Rankine scale, which does the same thing for the Fahrenheit, which 0 degrees on the Rankine scale is negative 459.67 Fahrenheit. So this would actually, negative 459.67 Fahrenheit is 0 Rankine on the Rankine scale.